Hello, I'm Wang from UCLA. Today I'm going to present our work on deep learning for graph similarity search. I'm going to first give a brief introduction and then talk about three of our recent projects. Graph has emerged as a natural data representation in many application fields. In a graph, there are nodes and edges representing entity and relations. For example, there are many applications of graphs in biology. On the left side, each node represents a protein, and edge represents the protein-protein interaction. It's a pairwise relationship. In the middle is a picture depicting such a relationship actually in different tissue type. It becomes a multi-layer, multicellular functional network. On the right-hand side, each node is a species, and the edge representing their dependencies of different species in nature. In chemistry, chemical graph has been used as one of the most popular representations for chemical structures to represent their either 2D or 3D structure. Graph has also been the underlying data representation for social network analysis. In social network, each node represents an individual, a person, and edge representing their relationship. Another area that we have seen more and more utility of a graph application is in software analysis, where each node representing either a function or procedure or data structure, and edges representing the relationship, either temporal relationship or functional dependencies. Last but not least, graph has also been extensively used in circuit design. Graph operation can be grouped at two different levels. First, at the node level, in which you have a single graph and you want to be able to predict either properties of nodes or edges. On the right-hand side, which illustrate the graph operation at the graph level, where you have a collection of graphs and you want to make prediction and inference on the graph, treating a graph as a unit. Our project belongs to the second class, which is graph level operations. We study graph similarity search. As illustrated here, given a pair of graphs, we want to compute what is the similarity between these two graphs, give a similarity score. A closely related operation is called graph matching, in which that you not only have a similarity score, but you want to find out which part of these two graphs actually match each other. In this illustration, you can see that actually the matching part is highlighted by the orange nodes. We're also interested in studying graph level representation for the purpose of similarity search or matching. The first project I will talk about is called SimGNN, which is a neural network approach to fast graph similarity computation. As I mentioned previously, we have a query graph, and we are giving a graph database. We want to find out which graphs in the graph databases actually have high similarity to the query graph. And the output will order all the graphs in descending order of their similarities, which means the most similar ones come first. This is a very challenging problem, as the absolute exact solution requires NP-hard complexity. Now the first question is on how to compute the graph similarity. On the screen I show you two graphs, and now the question is that how similar are they? One way to do so is by computing the graph edit distance. Intuitively, it is the number of operations that needed to convert one graph to the other, and vice versa. It is a symmetric relationship. in this particular example, you can see that the graph edit distance is 2, which means that you want to clip off this little branch with 6 and 8 and reconnect them to the node 7. So this would give you a graph edit distance of 2. Here are a few more examples of graph edit distance. On the top, actually the graph edit distance is 0 because these two graphs are essentially the same. Where in the middle, is the example that we just talked about where the graph edit distance is 2. In the bottom, actually the two graphs are very different. Their graph edit distance is 10. I want to mention is that the graph edit distance and the similarities can be converged into each other by a bijective mapping. So when the graph edit distance is low, that means the similarity is high. So when the edit distance is 0, the similarity is 1. So meaning that the two graphs are isomorphic. When the graph edit distance is high, then the similarity score is low. It's going to be close to 0. It is well known that the computation of exact graph edit distance between two graphs is NP hard. Therefore, there have been extensive work in developing a fast algorithm to approximate the solution. It's basically based on search and combinatorial optimization approaches. And many of these also incorporate domain knowledge and heuristics to speed up the search, and which sometimes is difficult to design. On the right-hand side, in the table, I show you a few representative approaches, and A star is the exact solution. You can see the time complexity is very high. And N1 and N2 are the size of the two graphs. Where on the lower part of the table, you can see there's a few algorithms that people propose that are faster, but it does not guarantee to give you the exact solution. On the bottom of the slides, you can see that actually this is showing you the to convert one graph to another from left to the right. That requires 3 steps. First, cutting one edge, and then connect to the dashed edge, and then change the label of the node. So that's require edit distance of 3 to convert from one to the other. What we hope to do is to develop a general learning framework for graph similarity search. Our goal is to learn a neural network-based similarity function phi. The input is a pair of graphs, Ji and Jj, and the output is the estimated graph-graph similarity score. So we do want to have a few desired properties of this similarity function. First, it needs to be representation invariant, and then we hope it to be inductive so that we can incorporate new graphs without retraining the model. We also wanted it to be learnable, to be adaptable to different edit distance or graph similarity functions. During the training phase, our goal is try to minimize the MSE loss between the predicted similarity and the ground truth. We are giving a collection of graph databases, and we want to do this, learn this function during the training phase. After the trained, we will go to the testing phase. In the testing phase, we want to give a pair of graphs, actually many pairs of graphs, and want to compute the graph-graph similarity using our neural network model. And hopefully that estimated similarity is very close to the true similarity. Now let's look at a little bit under the hood, how we do this. So the overall framework have 2 big components. On the left side is the encoder part. We first use GCN to encode at the node level, to generate at node level the embedding. And once we have the node level embedding of each node of each graphs. We next want to generate a graph level embedding through a attention mechanism. The high-level idea here is that we want to be able to, using the attention framework, to learn the important subgraphs of each graph that actually contributes the most to the similarity score. So after that, we want to be able to model the graph interaction, meaning like, well, if two graphs are similar to each other, right? So how similar are they, and which part of the graph actually shows the similarity? And there's two routes of doing that. And the first one is to just use the prior work on neural tensor network as illustrated on the top of this figure. And the second route is actually our novelty. Is we create a pairwise node comparison using the node level embedding. And we generate a matrix and also a histogram. We use this together with the output of the neural tensor network, concatenating together and fed into a few fully connected layer. And from that, we predict the similarity score. So I want to highlight the novelty of this work. The first novelty is on the attention-based graph level embedding that we introduce, and the second novelty is the histogram features that we generate from the pairwise node similarity. In our experiment, these two parts demonstrate that actually it can improve the performance substantially. First, I want to show you the comparison with a few existing methods, and in terms of the MSE and the rank correlation and precision at 10 and 20, you can see that our model SimGNN performed the best. It's more accurate than most of the existing approximate GED algorithm. Because in addition to the A-star, all the other algorithms actually are approximate algorithms. There's no guarantee they find the exactly graph edit distance between a pair of graphs. And so are our algorithm, that we also do the approximation, but we can approximate much better, much more accurately than of this existing approach. This figure shows that the running time of different algorithms, you can see that the exact solution A-star is the slowest. The y-axis shows the time in logarithm scale. It's also noted that our algorithm is slightly slower than most of others' neural network-based approach, but we are far more accurate than them. And for those search-based approach, like Beam, Hungarian, and VG, we are much faster. Here I show you an example to compare the result of our algorithm with the exact solution. On the very left side is a query graph, and after that, those are the results returned by the algorithm, sorting in descending order of similarity. You can see that for this small example, we almost generate the same result as the A-star algorithm, at least the first 5 of them. The first difference starts at the 6th one. Here's another example on a different data set. Again, this is compared with the exact solution A-star. You can see that actually we are finding the what exactly the A-star output. In this particular case, it happened to be there's quite a few isomorphic graphs existing in the database. That's why you can see that the graph edit distance is 0, and at least 6 of them here are identical. So we also find out exactly the same solution here. Now the question is that, can we even do better than that? And the answer is yes. Here's come to our second project, which is on learning-based efficient graph similarity computation via multi-scale convolutional set matching. The question we want to ask is, can we avoid generating graph level embedding altogether? Remember, in SimGNN, we have both node-level embedding and the graph-level embedding. So if we can avoid generating the graph-level embedding and somehow leverage the node-level embedding in a different way, then maybe we can get even better result. So here, as you can see that we have two sets of node embeddings. We want to turn that into a set matching problem, in the sense that we want to compute node-node similarity matrix in a way to encode the node alignment information between these two graphs. If two graphs are similar, intuitively, there exists a subgraph of each that actually have a close match of each other. So this can be reflected in a similarity matrix. So once we have a similarity matrix, then we turn the graph similarity problem into an image pattern recognition problem, because we can treat this 2D matrix as an image, and a certain pattern within this image can definitely indicating that actually there's a match between these two graphs. This figure shows the overall architecture of our new model GraphSim. We first applied GCN multiple times to obtain the node embeddings. In this figure, we show that we have applied the GCN 3 times. After that, we compute the similarity matrix of the node embedding between a pair of graphs. Here, because we have GCN 3 times, we are going to have 3 node embeddings for each node, and then we're going to compute the similarity matrix of each of that. So we're going to have 3 similarity matrices. This 3 similarity matrix is going to be fed into a convolutional neural network. Again, the CNN is applied to each individual similarity matrix and to generate the output, and then they are concatenated together to be fed into a multi-layer of a fully connected layer, and finally to predict the similarity. The reason why we want to have this multi-scale GCN is because we observe that embeddings may lose subtle patterns in local neighborhood after aggregating neighborhood multiple times. We can see from this illustration that we have 2 figures, A and B, 2 graphs A and B, and the only difference they have is in node 7, where on the left one, graph A has a blue color, and on the right side, graph B has a yellow color. And this can be reflected in the similarity matrix after each GCN. You can see that after first GCN, the similarity is very low between these 2 7 nodes. After the second GCN, you can see in the green color, it shows a little bit higher similarity because there's more neighborhood information being gathered. And the neighborhoods are identical, so that contributes to increase the similarity there. And after the third GCN, you can see that similarity is quite high. You can observe from this 3 similarity matrix that actually each of them contain valuable information at different scale, and we need all of them. That's why in our second phase, we want to compute the similarity matrix at each scale, and in the third stage, we want to apply the CNN on each of the similarity matrix and concatenate the result together to make the prediction. This slide shows the experimental comparison of GraphSim with the existing solution. The first one, A star, is the exact solution. You can see that we can only run it on a very small data set, but it gives you the exact solution, 100% accurate. The next 4, BEAM, Hungarian, VG, and HED are the search basis algorithm, and the next big group are neural network-based algorithm. This also include our previous model, SimGNN. The last one is our new model. You can see that GraphSim outperforms all these algorithms in terms of the MSE, in terms of the rank correlation coefficient, and the precision. Here is just an illustration of some of the examples compared with the solution provided by A star. And you can see the left one is the query graph, the right one are the result ranked by their similarity. Okay, the most similar ones ranked first, which means they have a distance 0. So you can see that it's the first 4 solutions provided by the GMCAN are the same as the A star. The only difference starts at the 5th one. So this is a pretty good result. On the bottom one, there's another data set. I believe this is a Linux data set. You can see they have, in that data set, they have quite a few isomorphic graphs. And both A star and the GraphSim are able to find those. Okay, so practically GraphSim delivers very promising results, even though it is still an approximate algorithm. On the lower left part of the slide, I show the running time of different algorithms. And as you can see that the GraphSim has comparable running time as other neural network-based solution, and much faster than the search-based algorithm, and also much faster than the A star algorithm. Well, the previous result shows that we can do quite well without generating graph-level representation. Now the question is that, is graph-level representation useful at all, or just because we didn't generate it in the best way? So in the third project, I'm going to briefly give you an overview about our third project, which is to learn inductive graph-level representation where graph-graph proximity. So there has been quite a lot of approach that generate graph-level representation learning. And we summarize some of these representative ones in this table. And we particularly want to illustrate that whether there's a graph-level embedding and whether that's unsupervised learning, and also whether the embedding is inductive or not. So, and in this project, we are proposing a new graph-level embedding approach that can be learned in an unsupervised fashion, and it's also an inductive model. It's called UGraph EMB. This is at the 10,000 feet level view that to illustrate the difference between different type of graph representations. The first part is that we generate node embeddings from the graphs. And we may be able to do node classification, link prediction, and also visualization. Right? It can be done in either supervised or unsupervised way. And the second group of graph representation learning method actually generate graph embedding model from the node embedding model, and use that to do graph classification, for example, and typically done in a supervised fashion. And what we want to do here is actually belong to the third class framework. So we have not just a graph, but a pair of graphs, and also a collection of graph pairs. From the node embedding model, we want to learn a graph embedding model through the modeling the interaction between the pair of graphs, and so that we can not only do graph classification, but we can also do similarity ranking and visualization of different graphs. This figure shows the overall workflow of our model. The key difference here is that when we learn the graph level embedding, we leverage the relationship between pair of graphs. We do not just aggregate the node level embedding into the graph level embedding, but actually we look at the similarities between the graph pairs. And now the question is that whether this is working or not. Here's some visualization of the embedding we generated on 2 separate data sets. And for the little circles in red and the numbers basically showing you in this embedding space where are those graphs located. And the graph number 1 to number 12 are illustrated on the right side. And you can see that this is quite intuitive to show you that actually similar graphs are indeed landed together in this embedding space. So if we use this embedding for graph classification tasks, and this is a comparison with other graph level embedding approach, and you can see across different data set, our model achieve either the best or the result comparable to the best approach. And this illustrated in a similarity ranking task. Actually, our model can do better than search-based model, which illustrate on the top of the slides. They're only able to find one isomorphic graphs in the database, but we are able to find 3 of them in the database. And this is a comparison with the rank correlation coefficient and the precision across different databases. And not surprisingly, we are better than other graph level embedding approaches. I would like to thank my collaborator, Professor Izhou Sen at UCLA, as well as our students who did most of the work. Thank you very much for your attention, and I'm happy to take any